Okay, so now we're going to get into the topic, very important topic of nomenclature in chemistry. And what we're referring to here in this particular topic is basically the rules for naming compounds, right? And in fact, not only for naming compounds, but also for writing formulas, right? So basically, you're going to learn how to name the compounds based on the given formula and vice versa. If you're given a formula, how do you determine if you're given a name, how do you determine the formula and vice versa? Okay, so that's what nomenclature is all about. And the rules for performing this kind of exercise has been established by an organization known as IUPAC, IUPAC, and it stands for International Union of Pure and Applied Chemists. So this is an international organization, of course, of chemists, and there's a particular division that meets, I don't remember, I think it's like every 2 or 3 years. And their sole purpose is to come up with new rules for naming compounds because, as you can imagine, in chemistry, there have been compounds that have been new compounds basically being synthesized every year. And very often, what happens is that a compound or 2 or 3 or many may have been synthesized and the current rules may not be sufficient in order to name these compounds. So therefore, these guys have to meet ever so often to consider new rules to accommodate these new compounds, right? So the rules that we'll be learning about are the more simpler ones that deals with, the relatively small inorganic compounds, all right? So why is it important for us to know these rules? Well, we could have a specific name for each compound, but of course, again, given the sheer volume of the number of substances that are known, it would be impossible for us to memorize the specific name for each one of them, right? So as stated here, if you were to do that, you'd have to memorize the names of 500,000 different inorganic compounds and 20 million organic compounds. So therefore, it's best to have a systematic method which helps us to basically determine or predict what the formula for a compound would be if we know the name, or if we know the formula, then we can basically, based on these rules and conventions, determine the names, all right? So that's basically what we'll be introduced to in this section. So the first group of compounds we're going to look at and apply these rules to would be compounds that are known as binary molecular compounds. Binary molecular compounds. So what do we mean by binary molecular compounds? Well, the term binary means obviously that the compounds are made up of 2 elements, all right? Now, these 2 elements can be in different proportions, but basically you have 2 elements per molecule or formula unit. Well, in this case, we're dealing with molecules, so 2 elements present per molecule. And of course, molecular compounds, we know that they exist as a collection of atoms held together by covalent bonds, and as a unit, the collection of atoms is called a molecule, all right? So how do we name these compounds? Well, firstly, we have to recognize that the name consists of 2 words, right? The first one is the name of the element that appears first in the formula, right? So the full name of the element that appears in the formula, that would be the first half of the name of the binary molecular compound. Now, the second word, you have to make some modification to the name of that element in order to include that in the name of this compound. So what you do in the second word is that you use the stem of the name of the second element and then end it with the letters IDE. So that would be the suffix that ends the name of the second word that would make up the entire name of the particular molecular compound, all right? And then after that, you may need to modify the name further by indicating prefixes to both parts, which indicates basically the number of atoms of each element present in a molecule, all right? So these are basically the steps that are involved in naming binary molecular compounds. And of course, we're going to look at some examples of how this particular rule works, all right? Now, this begs a question, and let me go back to this slide right here. Going back to this particular step right here where it says the first word comes from the name of the element that appears first in the formula. So this begs the question, how do you determine which element appears first in the formula? Well, you could memorize this chart, which I, of course, reasonably would not expect you to memorize it, which gives you basically the order of the elements in terms of which one comes first in the name or the formula. All right. So if you memorize this chart and go through the flow, you know, the direction of the arrows, that tell you the order. However, the rule of thumb that we use, generally speaking, is that we look at the relative positions of the two elements in the periodic table, right? And the one that is further down and to the left of the other one would be the one that is written first, which is usually the less electronegative element, all right? So for example, in the case of a compound containing arsenic and sulfur, which element is named first? Well, if you were to look at the periodic table, you'll see that arsenic is arsenic is above sulfur and to the left, right? Actually, no, arsenic would be below sulfur and to the left. So therefore, in fact, you know what? Let me go to, let me see here. All right, I won't, waste any time looking for the relative position. But basically, I know that arsenic comes before sulfur because arsenic is below sulfur and to the left. So therefore, arsenic would be placed first in the name and in the formula, followed by sulfur, all right? So that's basically how you determine which element is named first, the one that is less electronegative, all right? Okay, let me go back to full screen. Okay, now I mentioned the prefixes earlier, which will become important when it comes to getting the full name of the compound, because when naming binary molecular compounds, you have to also indicate the number of atoms of each element present per molecule, right? Now, what you're looking at here on the screen are the prefixes that are used when it comes to the number of atoms going from 1 to 10. And for all purposes, we'll be stopping at 10, even though we can actually go beyond 10, but we won't go beyond 10, right? So it's very easy to understand the relationship between the prefix and the number of atoms. Very simple: mono for 1, di for 2, tri for 3, and so on and so forth, all the way to deca for 10, all right? And some examples are given right here, all right? Now, one thing I should mention, which I don't have on any of the slides here, is that there's a specific rule when it comes to the first element, and there's only one atom of that element in the formula, right? And that is that when you're writing down the name of that compound, then no prefixes is used for that first element if there's only one atom of that element present, all right? So for example, in this, let me go to my pen function here. So for example, in this first example right here, right, you'll notice that the formula is NO, and of course we understand that there's a 1 here and a 1 here, right? Now the first element, of course, is nitrogen, and there's only one atom of nitrogen. So according to the rules, we do not use the prefix mono when it comes to indicating the number of atoms of nitrogen present. And the reason why is because it's the first element and there's only one atom. However, for the second element, you have a 1 here, and therefore you have to use mono for the name of that element, right? So therefore, for the first element, nitrogen, there's no mono. But for the second element, which is oxygen, we use the prefix mono, and then the stem of the name of the other element of the oxygen, which is ox, and then followed by IDE, right? So that's basically how we name this compound. The name of this compound would be nitrogen monoxide. Excuse me. And then in the next example, again, there's no mono for the first element because there's only one atom there. But of course, in the case of oxygen, there are 2 atoms. So therefore, the name of this compound is nitrogen. Again, there's no mono in front of the nitrogen. So it's just simply nitrogen, di, because you have a 2 here, and then ox for oxygen, and then IDE, all right? So therefore, the name of this compound is nitrogen dioxide, and it's not mononitrogen dioxide. In the case of the third example here, we have N2O3, right? 2 nitrogen atoms, 3 oxygen atoms represented here. So therefore, we need to use a prefix here because you have 2 atoms for the first element. So the prefix is di, and of course, the first element is nitrogen. And then for oxygen, the prefix is tri because you have 3 of them, tri, and then ox, and then ide, and therefore that's the name of the compound, dinitrogen trioxide, right? And if you understand that, then you should be able to understand what's happening in the rest of these, all right? So the key thing I would want to stress when it comes to naming binary molecular compounds is that, one, the less electronegative element is indicated first in both the name and the formula. Two, the second element always starts off with the stem, right? And then the IDE in the name, right? So all these compounds end with IDE in their names, right? The next thing I would say is that when it comes to the use of prefixes, that for the first element, if there's only one atom of it present in the formula, then no prefixes are used. So you won't use mono, right? For the second element, however, it doesn't matter if it's 1, 2, 3, how many, you have to use the appropriate prefix, all right? For the first element, going back to the first element, if you have 2, 3, 4, then you have to use the appropriate prefix, di, tri, tetra, etc. All right? Okay, so that's basically how we deal with naming binary molecular compounds. And I just want to point out a little information provided at the bottom of the table here. It says when the prefix ends with an A or an O, and the element name ends with an A or O, the final vowel of the prefix is usually dropped for the ease of pronunciation. For example, nitrogen monoxide, right? And not nitrogen monoxide, all right? So basically, that's something that you need to take into account as well. Okay, so let's move on to some examples. So it says here, write the formula and name of a compound for which the molecule contains 6 oxygen atoms and 4 phosphorus atoms. So here they basically give you the composition of the molecule in terms of the number of atoms of each element present. First thing you'd have to, of course, figure out is which element comes first. And again, as I said before, you'd have to go to the periodic table. And based on what I recall about the periodic table, phosphorus comes before the oxygen because the phosphorus is below oxygen and to the left in the periodic table. So therefore, the phosphorus starts off first, and there are 4 of them. And then it says 6 oxygen atoms, so we're going to put O6, right? So that would be the molecular formula for this compound. And therefore, the next part is asking for the name of the compound. The 4, of course, you have to indicate the prefix for that, which would be tetra. And for the oxygen, it's 6. So therefore, oh, by the way, tetraphosphorus. Can't forget that. Tetraphosphorus. And then the 6, the prefix for that would be hexa. And then because it's oxygen, the ending would be oxide. All right? So the name of this compound would be tetraphosphorus hexaoxide, or you can call it this. This is actually allowed by IUPAC. Tetraphosphorus hexoxide. All right? That's allowed as well. And so if you use this or this, they're just as correct. Okay. The next example is asking, it's a 2-part. It's asking in A part for the molecular formula phosphorus pentachloride. And that's relatively simple. The formula for phosphorus is P. Penta means 5. And of course, we know that the next element is chlorine. So basically the formula is PCl5. All right. And then in this case here, they're asking for the name of this compound. So in the case of this compound, the first element is sulfur, and the prefix for that would be di, because you have a subscript of 2 associated with that. So that's disulfur. And then the 10, along with the fluorine, would indicate that the prefix is deca, deca, and then the rest would be fluoride. All right, so that's the name of this compound, disulfur decafluoride. Okay, so those are just 2 relatively simple examples. So let's move on to ionic compounds and ions, all right? So let's talk about what we mean by ions first. So, and again, this is something you should have met before in your introductory chemistry, so this will be, again, a bit of a review. Excuse me. So, An atom that either loses or gains electrons is called an ion, right? So you can have, for example, sodium losing an electron to form a sodium ion, just as an example, or you can have an atom like chlorine gaining an electron to form a chloride ion. So those are just two simple examples. Now, what will happen when an atom converts to an ion is that there will be a change in the number of electrons, obviously. What will not happen is that there's a change going to be taking place between or within the atom, or I should say within the nucleus of the atom. So therefore, there will be no change in the number of protons or neutrons present in the nucleus of the atom. So in the case of an electron loss by an atom where there's no nuclear change, then you're going to end up with the ion having a positive charge, and that is called a cation, all right? On the other hand, if you have an atom gaining an electron or two, then basically the resulting species will have a negative charge, and it's called an anion, all right? So we have cations and anions being formed. Cations result from the formation of a positive charge resulting from the loss of electrons, while anions are formed when an atom gains electrons, all right? Okay, now, when you have an ionic compound, it's a result of very strong attractive forces that takes place between ions of opposite charges, right? And basically, the entire compound is an electrical neutral because the total number of plus charges will be equal to the total number of negative charges. And we can see that in the example of sodium chloride, right? So, and this is typically what you see in the case of an ionic compound. Basically, what you'll have are sodium or positive and negative ions arranged in a very ordered fashion. And in the case of sodium chloride, they're arranged in the way that we see it here, all right? And this underscores a very important difference between ionic compounds and molecular compounds, because as we saw earlier, molecular compounds exist as very discrete units consisting of collections of atoms held together by, by covalent bonds. That is not the case for ionic compounds. Ionic compounds do not exist as distinct or discrete units, all right? Instead, you have this arrangement, as I said before, this continuous arrangement, ordered arrangement of the ions, all right? And therefore, you don't have that discrete unit of a molecule of any ionic compound. So there's no such thing as ionic molecules, all right? So let's talk about monatomic ions in more detail so that we can understand how we can determine the formula and the names of these compounds. Now, some general observations can be made concerning the formation of monatomic ions based on the positions of these elements in the periodic table. If the element is from group 1A, then they tend to lose electrons to form ions of +1 charge, all right? And that is true from lithium all the way down to cesium in that group. In the case of group 2A elements, they tend to lose electrons to form ions of a +2 charge. Now, in the case of aluminum, which is in group 3A, they tend to lose electrons to form a +3 charge. And that is true also for some other elements in group 3, but things become a bit more complicated beyond aluminum going down that group. When it comes to non-metallic ions, which are formed from group 5, 6, and 7, then these tend to form ions which have charges of -3, -2, and -1 respectively, all right? And then we get to another complicated situation where we have elements in what we call the transition region. They're also called group B metal elements. In a lot of cases, for some of them, they can form ions with more than one possible charge, all right? And therefore, we have to take that into account when we're naming these compounds and when we're writing down the formulas. And the way we do that when we're writing down the formulas is that we use Roman numerals to indicate the actual charge that is carried by the particular ion, all right? And we're going to see some examples of that shortly. And then finally, there are a few of these same elements in the group B metal region that have only one common ion, right? In other words, they don't form ions of more than one charge. And we're talking about elements such as silver, zinc, and cadmium. And in those cases, we do not use any Roman numerals, all right? So if you have elements that can display more than one charge, then we have to use Roman numerals because we have to make a distinction to show which one we're actually referring to. But if we're talking about particular transition elements that do not display more than one charge, then we don't indicate the charge using Roman numerals because according to IUPAC, that's being redundant, all right? Okay, so with that said, oh, and by the way, let me just say this, and I should have had this up earlier, so forgive me, this is going to take some time. Let me go to the canvas. The same table I showed you, in fact, you know what? I don't need to do that. Hold on 1 minute. I think I have it saved here. Okay, yes, I do. Okay, so I've provided, I don't know if I made this point to you guys before, but it doesn't hurt for me to say it again if I've said it before. I provided some charts, which gives you some common ions that you will encounter in this course, right? Such as this chart right here. So it gives you all the common ions for different elements, including those that display more than one charge. As I mentioned earlier, such as titanium. Titanium can exist as +4. Let me make this larger so that it can be better seen. Okay, so I'm just going to highlight a couple of examples here. So for example, titanium, excuse me, can exist as +4 and +3. And the way we distinguish between them using names and using Roman numerals, we call this titanium 4 in Roman numerals, which is in parentheses, right? That's +4. And titanium 3, right? +3, all right? And that's basically how we indicate the charge on all of these ions that can display, these metallic ions that can display more than one charge, all right? Now, in the case of other ions that displays only one charge, then we do not use Roman numerals, right? So magnesium ion is just magnesium. Calcium ion is just calcium, and so on and so forth, all right? So this is one page, and let me go back to regular size. There's another page I've provided right here. Let me write this up, right? Which gives you some other ions, and some of the same ions I showed you before. And then here's another page, right? So basically, when it comes to naming ionic compounds or writing down your formulas, you'll be referring to these pages, all right? You'll have access to these pages so that you'll find useful. Okay, so let me go back to here. So based on what we have just covered, let's see if we can answer these questions. The first of which, it says determine the formula for calcium chloride, A, and for magnesium oxide, which is the B part. So let me go back to full screen here, and let me, whoops, sorry, go to my writing function. So in the case of calcium chloride, we do this one up here. What I would do, if I were you, is that, excuse me, I would go to the tables I just showed you, and I would look up the formula for the calcium ion. And if you look it up, you're going to see that the formula is Ca2+. And then you do the same thing for the chloride ion, and if you look it up, you're going to see that it is Cl-. Now remember I said earlier that for ionic compounds, the compounds would have to be electrically neutral, which means that the total number of plus charges must be equal to the total number of minus charges. So in this case, we have 2 plus charges, but we have a -1 charge here. So to get the charges electrically canceling out, we need 2 of these, right? So when you put these together, the resulting formula becomes CaCl2, and this would be the final answer. And please note, in the final answer, we do not write the charges. So these charges that we have here in the separate ions, you do not write them in the final answer, all right? So that's basically how that is done. And if you understand that, then you should be able to understand what's happening in this case, where magnesium, if you look it up, has a +2 charge. The oxide ion has a -2 charge. And in this case, the charges already will cancel out because we have 2 plus charges here, 2 minus charges here. So these 2 would combine to form MgO. And that would be the final answer. Okay, So for the second part here, in this case now they're giving you the formulas and they're asking for the names. So in this case here, what you would do is, and again, you can look it up in the charts here. The name of this element here is magnesium. And the name of this ion here would be the sulfide ion. So the name of this compound would be magnesium sulfide. Oops. All right. Now for this one here, what you'd have to do, you have to be careful with this one, because if you go to the table, in fact, let me come back here and go to the table I showed you earlier. You'll see that chromium, where's chromium? Chromium. Okay, not there. Chromium, where is chromium? Okay, so if you look at chromium, you see that chromium can exist as +2 or +3, right? You have chromium 3 and chromium 2. So now, going back to this, you have to ask yourself, which one of the chromiums would this be, right? And the hint in order to answer that question is that we look at the charge and the number of ions present here, the chloride, right? So if you go to the table, you see that chloride has a -1 charge. Let me go back to here. So in this case here, you'll see that there are 3 chloride ions, and each chloride ion has a -1 charge. And because the entire compound is neutral, that means that whatever the charge carried by the chromium here must carry a total of +3 charges, or 3 plus charges, right? So that these 3 plus charges will cancel out these 3 negative charges, right? So we have to figure that out. We have to figure out the charge on the chromium so that we can name this properly. So the name of this compound would be chromium 3 chloride. All right, and that's it. That would be the name of this compound, chromium 3 chloride. All right. Okay, so that's basically how we name binary ionic compounds if you're given a formula, or vice versa. All right, so what this is just showing you are basically some monatomic ions. I showed you them already in the table I showed you, but this is just basically showing you some of the same. And as I said before, there are certain particular monatomic ions that can display more than one charge, such as iron 2 plus, iron 3 plus, cobalt 2 plus, cobalt 3 plus, copper plus, copper 2 plus. And then there's some like zinc, silver, and cadmium that display only one charge. All right, so that's just basically just showing you, some monatomic ions and their charges. What else? So this is just asking a question. So what would be the charge on the zirconium 4 ion? Well, that's very easy. All you have to do is look at the Roman numerals here. That's 4. So therefore, the charge must be +4. Okay. Let me see here. So this is just basically, I think I mentioned all this before. But basically to name, it comes down to naming a binary ionic compound. We name the cation followed by the anion. All right. But the other thing you need to be aware of is that the combination of the anion and cation must be electrically neutral, which means that the total number of plus charges must be equal to the total number of negative charges, right? And also the formula unit, very important term here, which is basically the simplest collection of cations and anions that represents an electrically neutral unit, right? So, excuse me, in the example that I gave you before, for example, chromium 3 chloride, this would be called a formula unit, right? CrCl3. That would be the formula unit of chromium chloride. Not to be confused with a molecule, because as I said before, there's no such thing as a molecule when it comes to ionic compounds. Okay, so let me see what's happening next. Okay, so we're going to stop here. The next topic we're going to discuss deals with polyatomic ions, right? A very special group of ions. We have to deal with that, especially when it comes to writing down your formulas, right? So we'll stop here and get to that topic next time.